Hi everybody. Okay, so today we're going to start doing Lewis dot structures. And we've already started talking about these Lewis dot structures. We started talking about them a while ago. And what we talked about is that each dot represents one valence electron. So if we looked at, we'll start off with an element, all right? So if we looked at, for example, hydrogen. Hydrogen is 1s1, so it has one electron, one valence electron. So hydrogen's electron Lewis dot structure would just be H with one dot. So that's all. Super easy. And if we looked at carbon as an example, the electron configuration would be 1s2, 2s2, 2p2. Now we're only looking at the valence electrons. So the valence electrons, remember, they're the outermost, so that would be here, valence. So all we're looking at are these two. So therefore, our electron dot structure would be carbon, the symbol, and then the way that I taught you was the S's are up here, so two S's, and then carbon would be like this. All right? Now, once you learn how to do that, the next best way to do this would be to do your valence electrons this way. So we're going to go carbon, and then we're going to go 1, 2, 3, 4, and we're just going to rotate around. And the reason is because carbon, which has 4 valence electrons, can take 4 electrons or lose 4 electrons. And so it has 4 spaces for bonding. And so that's why we put the 4 dots this way. So when we draw a compound using carbon, it allows us room to put the 4 dots. So let's look at phosphorus, which is 1s2, 2s2, 2p6, 3s2, and then 3p3. Now remember, we're only talking about the valence electrons, so that would be these 5. And so what we're going to do is we're going to use this new method, and we're going to say phosphorus is 1, 2, 3, 4, 5. So you can see right there that phosphorus has 3 places for bonds. All right. Now nonmetals, as we're going to find out, they have the ability to expand their octet. And remember, the octet rule is that elements have the ability to gain or lose electrons in order to have a full octet. And you can see the octet forming here, right? It's forming here, the 8 electrons. But nonmetals like phosphorus and sulfur, they have the ability to have more than 8. And so you're going to see that as we go. So we're going to start today by talking about the electron dot structures for ionic compounds, and we've already done these. Remember, an ionic compound is formed from 2 ions. So that would be a metal and a nonmetal. Okay, and that's how you know it's an ionic compound. So when we form these ionic compounds, what we're going to do is we're going to take the element, we're going to transfer the electron, and then we're going to form the compound. So starting with something really simple like sodium chloride. Sodium, 3s1, has 1 electron. Chlorine has 7 electrons, so we'll make chlorine red. Okay, and so it has 7 electrons. There's its 7 electrons. So sodium is going to give its electron over to chlorine, and that is going to result in sodium with a +1 charge, and chlorine, which will now have 7 of its own, plus it will also have sodium's electron. So now chlorine has a negative charge. And the interesting thing here is that these two form a bond because it's an ionic compound because of the positive and the negative. So then you crisscross, as you know how to do, but it's the positive and the negative that form the bond, not the transfer of the electron. So they form a bond, and what their bond looks like is this. So you have sodium, and then you have this bond between them, and then you have chlorine. I'm getting my pens all mixed up here. And then you have chlorine. Now you can see chlorine, this has 6 around it, but this line right here represents 2 electrons. So that line represents 2 electrons. That bond represents 2 electrons. So whenever you are making Lewis dot structures, the line, the bond, represents a pair of electrons. So sodium chloride looks like that. And so if you have to do an ionic compound, you don't have to show all of this here, the transfer of the electrons, but you do have to show all of the lone pairs. These are called lone pairs. They're non-bonding pairs, and they allow that octet. So chlorine still has that octet. Sodium doesn't have the octet because sodium lost its 1, and it has an octet underneath that, but we don't show that because it lost that entire energy level. Okay? All right, so now what we're going to do is we're going to go into covalent compounds. Now, covalent compounds are a little bit different because since, as we've discussed, these are made up of a nonmetal and a nonmetal, and they have no ions. What they do is they share valence electrons. They share them. And since they have no ions and they share valence electrons, what we're going to do is we're going to take all the electrons and we're going to put them into a pot, and then we're going to divvy them up to make sure that everybody has access to 8. All right, so there's some rules. There's some rules to doing this. So you're going to want to take down the rules so that you have them. All right, so number 1, hydrogen is always terminal. Terminal meaning end. It's always at the end. And if it's always terminal, that means it only has 1 bond. All right, and so you'll never have 2 bonds coming off of hydrogen because hydrogen only has 1 electron to give and only has 1 place for bonding. Number 2, the atom with the lowest electron attraction. There's a word for that. Think about that. Electron attraction. Who has the lowest electron attraction? That would be the lowest electronegativity. The lowest electronegativity is in the center. So the easiest way to think about that is it's going to be the one that's farthest to the left or down. So it's going to be farthest to the left or to the bottom. But remember, it doesn't include hydrogen because hydrogen can't be in the center, right? Because it's always terminal. Number 3. Find the total of all of the valence electrons. You're going to add them up. You just add them all up. Number 4, divide by 2. And when you divide by 2, that gives you the number of electron pairs, which would be bonds. Or lone pairs. So that gives you the number of electron pairs that you're dealing with. Number 5. Place one bonding pair between the central atom and each terminal atom. So that would be like if you were doing carbon with 4 hydrogens, you would put one bonding pair between the carbon and each hydrogen, and then subtract them from the total. Next, use the remaining pairs to satisfy your octet rule. So in other words, all your atoms must have 8 around them or access to 8. So they can be lone pairs, or double or triple bonds. And I'll show you how to do that. Lastly, excess electrons go around the central atom. As lone pairs. Okay, because some of those nonmetals can expand to have more than 8, right? We talked about that. All right, so let's look at an example. Let's look at something simple like methane. So that's CH4. Okay, so first I'm going to add up all my electrons. I have 1 carbon, which has 4 valence electrons. And I have 4 hydrogens, which each have 1. So that's 4 electrons. 1 each. 1 each, right? So that's a total of 8 electrons. So I divide by 2 is 4 pairs. Now I look on my periodic table. I know that hydrogen is terminal, so therefore carbon has to be the center. So carbon goes in the middle. Each one of the hydrogens is going to go on the outside. Most of these that you're going to get are either a straight line or a wheel. And then I'm going to put, next, I'm going to place number 5, place one bonding pair between the central atom and each terminal atom. And then I'm going to subtract that, so that's 4 pairs, so now I'm down to 0. And actually, I'm done. The carbon has access to 8 electrons. Those 8 electrons are 2 in each one of these pairs, so carbon has access to 8. See that? And hydrogen has access to 2, which is all hydrogen needs because hydrogen is a 1s, and so it's full with only 2 electrons. So this is what methane looks like, CH4. All right, so I'm going to use the same instructions, and I'm going to look at ammonia, which is NH3. That's my compound. So the first thing I'm going to do is I'm going to count up my electrons. I have 1 nitrogen, and I have 3 hydrogens. So my 1 nitrogen has 5 valence electrons. My 3 hydrogens are going to give me 3 electrons. So that's a total of 8 electrons divided by 2 equals 4 pairs. I look at the periodic table, but I don't even have to because I know that nitrogen is terminal. So therefore, that I know that hydrogen is terminal. So that means nitrogen will be in the middle. So I'm just going to do this because each hydrogen will have 1 bonding pair attached to it. I subtract them, which leaves me with 1 pair left. Now, according to my instructions, I'm going to use my remaining pairs, number 6, to satisfy the octet rule. I can make lone pairs or double or triple bonds. So hydrogen is completely satisfied, so I don't have to do anything with that. But nitrogen only has access to 6 electrons. It needs 8. So I'm going to use my last pair to put up there, and that's going to give me, nitrogen now has an octet. So everybody has access to the number of electrons they need. Okay, next, let's look at nitrogen trifluoride. So here we go. I have nitrogen, which has 5, and I have 3 fluorides, and each one of these has 7. So if you don't know that, go to your periodic table and see how many electrons does fluorine have. So each one has 3. Each one has 7. So that's a total of 21 electrons, right? So that's a total of 26 electrons divided by 2 gives me 13 pairs. All right, so I look, and nitrogen is farthest to the left, so it's going to be in the center. Again, you can kind of figure this out because remember what I said about the wheel? So the center of the wheel and then the spokes of the wheel, right? So here's my nitrogen and 3 fluorines. I subtract 3, and that leaves me with 10. All right, so now I look and I see each fluorine only has access to 2, and it needs access to 8. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then nitrogen only has access to 6, 10. So there are my 10 pairs, and that is what nitrogen trifluoride. So there are 10 lone pairs here, 10 lone pairs, and 3 bonding pairs. See that? Okay. Okay, next we're going to look at carbon dioxide. Okay, carbon dioxide, 2 nonmetals, right? So this is a covalent compound, so are these, right? Okay, carbon dioxide, so I have 1 carbon, which has 4, and 2 oxygens. Both oxygens have 6 each. If you don't know, count across from the left to 6, right? So that's a total of 12, which gives me a total of 16 electrons. Divided by 2 equals 8 pairs. Okay, so carbon is going to be in the middle. It is the farthest to the left, but also this is a wheel. So since you have 2 oxygens, you're going to need to put it in the carbon in the middle. Next, I'm going to connect the carbon to the oxygens by 1. Next, I'm going to put the 8 around the oxygen so that each one of my oxygens have an octet. So I have 1, 2, 3, 4, 5, 6, 7, 8. Wait a minute, I've used all my pairs. So now I'm in trouble because my carbon here only has access to 4 electrons. My oxygens are okay, but my carbon only has access to 4 electrons. Now remember what I said about in covalent bonds, they share. So what we're going to do is we're going to take this pair and we're going to put it in here, and we're going to take this pair and we're going to put it in here. And so the carbon and the oxygen will share those electrons. So what we end up with is carbon and oxygens sharing those 2 pairs. And when they do that, oxygen now has access to 8 and carbon now has access to 8. Remember, each bond represents 2 electrons. So remember, each bond represents 2 electrons. So if I add up my electrons, 2, 4, 6, 8, 10, 12, 14, 16. So how did I know to do that? Well, I knew that I was coming up too short on this side and too short on this side. So I can use these 2 pairs to double bond it. So that works out great. All right, next. What about PCl5? Okay, same thing. 1 phosphorus and 5 chlorines. Each chlorine has 7, so that's 35 electrons. And then the phosphorus has 5, so that's a total of 40. Wow. Divided by 2 is equal to 20 pairs. That's a lot of pairs. So let's see how we do. So clearly, this is a wheel. Phosphorus goes in the center. So then I'm going to put the 5 chlorines around. All right, so chlorine, 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 chlorine. And you could say, wait a minute, now phosphorus has 10. But remember, the last rule here was that the excess electrons go around the central atom as lone pairs. The reason is because nonmetals, phosphorus and sulfur and selenium, some nonmetals have the ability to have an expanded octet. So how do you know which ones? Well, your problems are going to be fairly obvious. So in this case, there's no other way that this can go. And the reason is because chlorine has 7, and so it can only form 1 bond. It can form more if it's the center, but it's not going to be the center here because phosphorus is farther to the left than it is. So it's not going to be the center. And so since phosphorus is the center, that means these chlorines are all around. So you can't put chlorine with 2 because that would make chlorine in the center, and it has the highest electronegativity between phosphorus and chlorine. So now that's 5, so I'm down to 15. So the next thing is I have to put electrons around chlorine because phosphorus is more than full. So electrons around chlorine, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's phosphorus pentachloride. All right, so this is very basic. I'm going to give you very easy ones for homework and then more naming problems. Now, if you're not doing the naming problems, well, you need to be doing the naming problems in the balancing equation. So I'm going to kind of mix your homework up so that you can do a couple of these easy ones. Follow the rules. Just read the rules and follow the rules. And so it'll kind of be a mixed assignment, and then you'll submit that to me online. Okay.